Okay, so last time we were talking about surfaces. And so here's 3 different examples of types of surfaces. I've drawn 2 of them. The other one I'm just struggling drawing. You can look in the pictures in the book. Let's take maybe the easiest example would be a cylinder here at the bottom. And here we've parameterized it. So suppose you have some curve, right, beta. So that's just like a curve in the xy plane. Imagine what I've drawn at the bottom there is the xy plane. Then what you can do is say, let u, what is the surface? The surface is 2-dimensional, so it has 2 parameters. It's like latitude and longitude, right? And the latitude, or the u, right, that's telling you where you are on that curve at the bottom. And then the v tells you how much to move up, right? And so in this picture, q would be a vector pointing this way, like up in this picture, right? And so you move along the curve, and then v tells you how much to move above the curve, right? I think that one's pretty easy to visualize, right? And then another example would be a cone. Everybody knows what a cone is, right? That's a circular cone, but it doesn't have to be a circular cone. You can actually have any curve here. So this curve right here would be delta of u. Think of this as the origin, or this is actually the point P here, but yeah, so that's the point P. But then what you do then is, let's suppose P equals 0, so we can just understand this. Okay, so imagine P is the origin, right? And you have some curve, let's say, above the origin. Then if V equals 1, you just get the curve, right? But if V equals 2, you get the curve. You stretch that and blow it out by a factor of 2, right? You can see that's going to give you a cone, right? And one thing that's interesting about these 2 examples is they're made up of lines. You could make them with pencils, like, or what do you call it? You ever see people make, it's like a kindergarten activity, you use popsicle sticks, and you make stuff out of popsicle sticks, right? You can make these out of popsicle sticks, right? Because, that's a straight line, that's a straight line, that's a straight line, that's a straight line. These are all straight lines here, right? Do you all see that? This is popsicle stick art, all right? Now, why is that? Well, because when you vary v in both cases, right, like hold u fixed, right, and vary v, you see this is the equation of a line. You have, remember u is a fixed constant, right? So that's a fixed constant. And when you vary v, you just have a vector, or you can think of it as a point if you like, plus v times a vector. V is a real number, right? That's the equation of a line, isn't it? So when you vary v, you get a straight line. And so all it's required is that there's this exposed v here. And so the more general of these 2, when you put it together, is there's your v, right? And you'll see that these are called ruled surfaces. They're made out of straight lines. And but why not have a combination of these where the starting point, here the starting point has to be the same for all the lines. Here the direction you move along the lines have to be all the same. They're all a bunch of parallel lines. But if you remove those assumptions, then you get something of this form here. And then notice, in other words, any function of u, or it's a vector, right? But any vector valued function of u plus v times any vector valued function of u, again. It's a ruled surface. Why? Because if you hold u fixed, that's a point, that's a vector, right? I mean, vectors and points are really the same thing, but you can think of it as a vector here, a vector there. But when you start at a base point plus v times a vector, that's the equation of a line, right? And so those are ruled surfaces. And if you look in your book, you'll have a picture of a helicoid. I haven't mastered the artwork of how to draw a helicoid, or at least if I did, I've forgotten how. So that's kind of cool. That's like your DNA helix kind of stuff. As more examples of surfaces, yes.
So for the cylinder example, you're saying that beta of u is like the point on the base that you're mapping, and then the v times q is the vector that traces that like up to the top.
Yeah. So if v is 0, you just get beta of u. If v equals 1, then you just take then you would come up to the vector v here. Whoops, I didn't draw that right. But anyway, you come up to the vector v here, exactly the vector, right? Just add v to it. Add q to it. And then if it's 2, you go up twice the height, right?
Okay. And then that gives a volume.
That gives a cylinder.
Cylinder. Yeah. Gives.
Right. So what we're doing is this will trace out points on the surface of that cylinder, a 2-dimensional cylinder.
Thank you.
Mm-hmm. So these examples are worth contemplating. Examples are really valuable. And now this leads us to the next section called the geometry of surfaces. It's starting to get really interesting here. And So here's our surface in 3 dimensions. And at every point here, there is a tangent plane. And I picked the point at the top because it's easiest for me to draw the tangent plane, easiest for us to visualize, right? But you all see that plane that just sort of, it's tangent to the surface, right? And we need a definition for it. We call this thing T sub P of M. That is, if the surface is M, and this is the point P there, then the tangent plane to M at the point P, we call that T sub P of M. And the definition is, it's a collection of vectors, right? It's all these vectors here, right? And so we say it's the collection of vectors V such that V is the velocity vector of some curve in M, at the point P, okay? So what does that mean? Imagine, so for example, here's a curve, right? Imagine this curve here, and it goes through P like this, right? And some curve on the surface, at some point, that could be its velocity vector, right? So just imagine all the curves that go through the point P, right? All curves in M. M is our universe. You're an ant walking on M, right? The surface of a potato. And now imagine all possible curves that are in the surface of the potato that go through the point P. What are all possible velocity vectors at that point? Answer, the tangent plane. Isn't that a nice way to understand the tangent plane? And you know what's particularly nice about it is it's an intrinsic geometry definition. Because if imagine we can start talking to this mathematician ants on this 2-dimensional surface, and suppose they have a whole civilization and mathematicians and physicists and all kinds of stuff, but they're completely oblivious to the 3rd dimension. I mean, they're very smart, but they're blind. They have feelers, they can put down markers, they do geometry. They know more geometry than any of you guys in this room right now, right? They're geniuses. Genius ants. And then somehow or another we start talking to them, right? And they would understand the notion of a velocity vector, right? They would understand that perfectly well. It's the direction I'm going when I'm going somewhere. Right now, they would visualize it differently, perhaps, right? But that definition makes sense to them because they know calculus. And now, you might wonder though, how do you even prove that this is a plane, right? Like the set of all velocity vectors, how do we know it's even a plane, right? And that follows from essentially the chain rule. So if we could look at all possible curves. So I remember how we define a surface as a local coordinate chart. So I can come over here. That'll be the UV axis. We have a rectangle here. We map that over there, right? And this is x of u comma v. And then we can have some curve over here. So any curve over here, which has, let's say, it has components u of t, v of t, right? So you all agree, I could call that alpha of t, but let's just say u of t, v of t, right? U and v are functions of t. Some curve over here, we compose it with this mapping over here, and so then we're going to get some curve over here, which we could call alpha of t, is equal to x of u of t, comma v of t. Right, so that's the point, is all of our curves are going to be of that form. Does that make sense to everybody? And so then you say, okay, what are all possible alpha prime of t? By the way, let's suppose that alpha of 0 equals p. Okay, so I want them all to go through the point p. So really what I want to know is what are all alpha prime of 0, right? So if alpha of 0 equals p, right? Then I want to know, and maybe that point p corresponds to this point here, right? Which we could call u naught comma v naught, right? Yeah, it's u of 0 comma v of 0. And so, if we do this computation, then we have to use a chain rule. It's just calculus, right? Y'all remember the chain rule? Multivariable calculus chain rule? If not, you become an expert on it? Yes?
Are we doing this at 0 because that's where we find the tangent plane?
Yeah, because we're trying to find the tangent plane at the point P, right?
Yes.
And these curves are only at the point P when t equals 0.
Okay.
Yeah. And so what we get then is just applying the chain rule. Now, there's notation here. How do you write the partial derivative, right? And this function x is a function of u and v. So I'm going to write x u. This will mean dx du. You guys get the idea? And then x v, that's what will mean dx dv. Okay, that's just notation. Just use as less chalk. Okay, and that was the standard notation of this book. And so, in other words, you look at the derivative in the first slot, right? Now, this is still a function of u and v, right? So you take the partial derivative of x in the first slot times u prime of t. Do y'all remember that, right? Plus the second derivative in the partial derivative in the second slot times the derivative of that second slot, right? Which is v prime of t. That's the chain rule. That's the multivariable calculus chain rule, which I'm going to assume you guys are all experts at. Okay. I know internally each of y'all are freaking out a little bit because you're like, oh yeah, I remember that, kind of, sort of, right? But let's just make sure we get the intuition of why the chain rule is true, right? It actually makes perfect sense, right? The point is, it's just a lot to keep track of, right? But become an expert on it if you're not already. We have a function, a composition of functions, right? And the point is that when we change t, this x of u of t comma v of t changes for two reasons, right? There's two different ways it changes. It changes because when t increases, when t changes, u of t changes, and then that causes x to change. And then when t changes, v of t changes, which causes x to change, right? And that's why we have two terms, okay? So the first thing is, okay, well, how much increase do we get when u changes, right? Well, x of u tells you the rate of increase of x when you increase u by a standard speed, 1, right? This is the rate of increase of x in the u slot. Well, how much did u change? This much. That's the rate at which u is increasing. Okay? So you have to multiply it by the amount that u, because if u prime of t was 0, u's not even changing. Of course, you should get 0 for that first contribution, right? And then the second thing is this x of v, this is the rate of change of x when you increase v. Well, how fast is v changing? That much. So you multiply by how fast it's changing. So the chain rule actually is, if you study it enough, makes sense, right? And they also look at the rigorous proof. And so that's the way I approach mathematics is like, I look at the rigorous proof, sure, but actually what's more fundamental to me is making it make sense. Like, is that plausible? Example, counterexample. When you're proving the chain rule, by the way, the simplest example would be the single variables chain rule. And I'll just fixate on this for a second. Let's say you have f of g of t, right? So these are just real value functions here. Let's just keep it super simple, right? Then the chain rule tells you that h prime of t is equal to f prime of g of t times g prime of t. Okay. And why does this make sense? Well, I mean, sort of when you change t, this causes g to go up, and then when you change the variable you put into f, that causes f to go up, right? And so, what's the rate of increase of this when you change t a little bit? Well, what's the rate of increase of f when you change g? That's what this is, right? Well, how fast is g increased? That's what that is, right? And then if you want to write it in the way where, like, getting closer to the proof, but also makes sense sort of in the middle, this is saying, before you take a limit, this is dh over dt is equal to, delta h over delta t. Remember, you take a limit as delta t goes to 0, that's h prime of t, right? This is delta f over delta g times delta g over delta t. And if you look at that, it's like, well, yeah, obviously it's just algebra, right? Whoops. Yeah. And then the fact that f equals h here on the outside, right? So you cancel this out and saying the change in f with respect to t right over here is the same as the change in a, because f equals h. Okay? Yes?
What if delta g is 0?
What if, well then this proof doesn't work, does it? And so this is, let's call this a mnemonic device, how I remember what's true. More than anything, right? So this is sort of in the middle of how I remember it and an actual proof, okay? So now if delta G is not 0, then this is a proof, right? But if it is, as you point out, I just divided by 0 there, so that was a nice question, right? Now how do you actually prove the chain rule? What you do is you step 1, prove it for linear functions. What's a linear function, right? A linear function would be, imagine if f of t equaled at plus b, right? And g of t is equal to ct plus d, right? And then that means h of t, when I compose the two, it's f of g, right? So it's going to be times, excuse me. Let me not skip steps. Let's define h of t to be f of g of t, right? And so then that would be equal to, see, a, then I plug in a g of t, ct plus d, right? And then plus b, right? Did I do that right? Mm-hmm. Which equals ac t plus some stuff, ad plus b, right? And then what you see is that the a right here and the c right there multiply to get ac, so that the slope of h of t is the multiplication of the slope of f times the slope of g, right? And it's saying that, so there was the slope of this, it's the slope of that times the slope of that, right? So we're seeing that explicitly, right, with linear functions, right? Guess what? The theorem is only true for things which are first order, right? So I really like that. Let's really look how about we just prove things for smooth things, right? You can take as many derivatives as you want. They're nice and smooth, right? Smooth things can be well approximated with linear approximations. Okay? So the point is, this is true, exactly true for linear functions. And guess what? Everything is well approximated by linear functions. To first order, in fact, everything is a linear function, right? It's like a Taylor series thing, right? If I draw a curve here, right? This curve is extremely well approximated. You see how for small values of t there, right? The linear thing approximates it extremely well. In fact, its derivative is the same. The slope of this curve here, slope of this line, the slope of that curve are the same there, right? And so if I can prove an identity, so then what you do is essentially the chain rule, the first step I'd say is look at these curvy curves, but they're all smooth. Approximate them with their linear approximation. Prove the chain rule for their linear approximations, right? And done. Because the slopes are all the same, right? The slope of this and the slope of this linear approximation are the same thing, right? So it really kind of comes down to showing that the chain rule is true for linear things, and then saying, oh, by the way, it's also true for things that are well approximated by linear things. Okay. So that's a nice little trick. That's the actual proof. So now, what I'm hoping y'all are walking away from here, if I've sort of dwelled on the chain rule a bit, is the first step is not understanding the proof. The first step is convincing yourself it's true. Like, look for a counterexample, right? And then you're like, oh, wait a second, and then I can't find it. Oh, why can't I find it? Oh, yeah, of course, because it actually makes sense, blah, 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 right? You do some linear, you look for examples. What's the simplest example? Oh, it checked out for linear functions, right? Oh, okay, and the next thing you know, you say, well, what if something was well approximated about linear functions? That gives you a rigorous proof. So that's a good way to think about how to approach mathematical proofs. Okay, getting back to geometry. We're talking about the tangent plane, right? And we want to show the tangent plane is in fact a plane, right? We defined it, right, to be the set of all velocity vectors to curves that go through the point P. And then what we can see here is that this first thing here is a vector, actually. X is vector valued, and so this vector right here is just, it's some vector, x. Oh, by the way, this is all at t equal to 0, right? And so this is, you take xu, and you got u of 0, v of 0. That vector times a real number, u prime of 0, plus xv of u of 0, v of 0, times v prime of 0. And so, in other words, this is, some first vector v times a plus the second vector w times b. V, well, this is the equation of a plane. That V is defined to be this, and the W is defined to be that. And my A and B are U prime is 0 and V prime is 0, which could be, I can choose to be whatever I want. Right, they're simply the rate of change of the curve, right? Through here, I could get U is 0 to be anything I want. I mean, U prime is 0 and V prime is 0 to be anything I want. And so this is, so what we see then is that these two vectors here, in fact, what's true in the similar proof is that any two vectors you choose, and of course from linear algebra we know any two vectors in a plane define the plane, as long as those two vectors are linearly independent, right? And then the rest of the plane is just linear combinations of that plane. We see that this plane is linear combinations of these two vectors, but then my linear algebra, as long as these two vectors are linearly independent, in fact any two of these vectors in this plane will define the plane. Okay. Any questions? And there's the proof is written out in the book with a little more formally, but this is the proof there. Now let's talk about the geometry that the ant can understand. It's very interesting to understand the geometry that the ant can understand. Like, what is it that we can do that doesn't require 3 dimensions? And so the ant can understand directional derivatives. So in other words, if I have a vector v here, okay? So v is just, what does that mean? It means it's the velocity vector of some curve that goes through the point P, right? At the point P, it's the velocity vector of the curve. We can take, and we have some function g, we can take the directional derivative. Now, what are some other notations you may have used before? I don't know, but we're not going to do those anymore. Some of them are okay, some of them not okay. All right, this is the directional derivative of a vector v when you apply it to a function g, right? So this is a vector, this is a function on the surface, right? Function on the surface. I'll say on M, okay? M is the surface of the potato. On the surface. Okay. And it turns out that here's the definition. It's going to equal, well, this is how the ant would think of it. You'd say, well, look, I know that there's some curve alpha of t. And this curve, let's suppose that alpha of 0 equals the point P, and alpha prime of 0, that equals the vector v that you're talking about, okay? You guys get the idea? So this is your alpha of t here. It's going through, alpha p here is equal to alpha of 0, and then v is alpha prime of 0. And so now imagine, if I want to do a directional derivative, what I would do is I would say, well, look at the value of the function along the curve. This makes perfect sense to the ant. The ant understands what alpha of t is. That's the curve, right? The ant understands what this function g is along the curve. So the ant understands a function of t. That's single variable calculus. So I could call that g of t if I wanted to. G of t is g of alpha of t. Okay, it's just what is the function g along the curve? Alpha, right? And so, therefore, I can take d dt of that. That's single variable calculus. And then I can say, well, what's the derivative of that at t equal to 0? And that's the in other words, what's the rate of change of a function along the curve that goes to the point P and has velocity v? Does that make sense to everybody?
Could you repeat that last part?
Yeah. What is the rate of, so in other words, I have some, think of G as like the temperature on the surface of the potato or whatever, right? And now imagine an ant walking along this curve. T is the time. When t equals 0, you get to that point P. What's the rate of change of temperature as you pass through the point P? That's going to be the directional derivative in the direction he's moving. Right? Those two notions. And by the way, when we use our single variable calculus, we can apply the chain. Well, now I'm about to use R. That's the definition. But now let's use R3 reasoning. We know from multivariable calculus by the chain rule that this is equal to the gradient of G, right? Evaluated at the point P, dot product alpha prime of t. alpha prime is 0 since t equals 0, right? Which equals the gradient of g dot product v, because alpha prime is 0 equals v. So, and this is probably how they define the directional derivative for you before. You say just take the gradient of the function dot product with the vector, right? So this definition agrees with your previous notion of directional derivative. But it's more fundamental because, see, this doesn't make any sense for the ant. Because when you compute the g, because, I mean, how do you even represent v? V is like a three-dimensional vector for us, right? What's g? G is a function of x, y, and z for us. It happens to be restricted to a surface, right? So when I write gradient of g, this is a three-dimensional vector dot product another three-dimensional vector. That's how we would think of it, right? So we can't explain that to the ant. It's like, what are you talking about? What's this third dimension? Right? So that's why this should be the definition. It's the derivative. By the way, and it doesn't require the notion, a fancier definition. It really is just that. It's just look at the function along the curve and take its derivative with respect to the time parameter of the curve. So if you do this, by the way, one consequence is let's take xu. Y'all remember what xu is? Xu is the partial derivative of x. We have this coordinate chart here, right? And I erased my picture a little bit, right? But put it back in here. Where we have a coordinate chart, right? V, u. This mapping x of u comma v gives us a rectangle, which I won't draw, but say the rectangle includes the point P, right? And then xu is the partial derivative. In fact, you know, I don't know. Let me just draw another picture. The picture gets sort of complicated, and then it's like, okay, so we have some rectangle here, right, that goes around like this, right? Here's your point P. Here's your tangent vector, your tangent plane, right? There's your point P. And so, you know, xu is going to be some direction, and xv is going to be some direction. So maybe this is xu, maybe that's xv. In fact, in general, when you look at the tangent plane, in general, xu and xv are going to be the easiest way to come up with a way of defining that tangent plane. And I gave some examples. I gave an example last time with the sphere. Remember, we computed xu and xv, I think, in one or two examples. And once you have two vectors, that defines the plane, right? As long as they're linearly independent, then that defines the plane. So when you say, what is the tangent plane? Typically what someone will do is you would start with your parameterization x of u comma v. And you would just compute xu and xv, and we know that those are tangent vectors, and then therefore linear combinations of them span the tangent plane. And so then what we might want to do then is say, well, what if we take a directional derivative of some function f in the direction xu? Okay, let's just apply that, right? Well, we have a definition of directional derivative. What we need to do is we need to find a curve where xu is the velocity vector. Okay. Well, the way you do that is, guys, look at this. Okay. We'll suppose this point P here is equal to x of u naught comma v naught. Okay. So when u equals u naught and v equals v naught, that's the point P. What if I hold v fixed, right? And now I vary u here. Okay. That's a curve. Y'all see that this is a curve? And this is a curve. And guess what? What's this velocity vector? It's a curve on the potato that has velocity vector xu, doesn't it? Okay. So that's my alpha of t, but it's alpha of u. And then we can simply evaluate the function there. And then what we're going to do is take ddu of that, actually, because u is my variable. And then evaluate it at u equal to u naught. And guess what? That is the directional derivative of f in the direction of xu, isn't it? By definition. Okay. By the way, we'll be using that fact a lot. I mean, very often you'll have a function. So what do you have to remember? What you have to remember, what is? Okay, so here's the thing to remember. If someone says take the derivative in the xu direction, remember, okay, so in other words, with this, let's go one step further. If I think of, if I write f as a function of u and v, okay? So there's something called abusive notation, okay? Because f is a function of x, y, and z, right? But the point is x, y, and z are functions of u and v, right? So we can say this is equal to f of x, right? Of u comma v, right? Everything, I've not used notation yet. But sometimes it's just convenient. Then just to kind of write this as f of u comma v. It's just kind of handy dandy to do that sometimes. Now we've abused notation. F is not a function of u and v, it's a function of x, y, and z. Right? And so, if we were being, want to be pedantic about it, we'd be like, wrong, you can't do that. Right? Okay, fine, I'll put a tilde there. Are you happy now? Okay, technically it's a different function. But the point is, I want to think of the, okay, f tilde and f are the same thing, except here I've expressed it as a function of x, y, and z. Here I've expressed it as a function of u and v. Okay, now are you happy? Right? And then sometimes you just don't put the tilde in there. It's just annoying. Okay, we just expressed it in terms of other variables, right? Okay, so the point is that what this equals, I'll do it without abusing notation then, this is equal to what's inside here, right, is actually f tilde, right, of u comma v naught, and then you take d du of this, and then evaluate at u equal to u naught, which is another way of saying, oh, it's just f tilde, take the u partial derivative, so we'll put the u subscript, u naught, v naught. Okay? So in other words, when you have a function f, and you want to take its directional derivative in the direction of xu, just express the function f as a function of u and v, and it's the partial derivative in the direction of u. Which, by the way, I think makes sense, right? This is saying take the derivative of f in the direction that where u is increasing and v is not changing, right? xu means increase u but don't change v. But this means increase u and don't change v. It's the same thing, right? Partial derivatives mean take the derivative in the u slot, increase u but hold the other variables fixed, right? So they mean the same thing, and so yeah, thank God. I mean, they are equal, in fact. So this is actually very useful, and you're going to be doing a lot of calculations. It might even be in your next homework. So yeah, pay attention to that. Let me tell you something we don't know how to do yet. And we'll figure it out later in a couple different ways, but it's sort of interesting to understand that, like, what you can do with intrinsic geometry and what's easy and what's hard. This is actually pretty straightforward here. Y'all get the sense that I don't know, when I was a student, it's like, oh, okay, yeah, whatever, it just makes sense. Oh, okay, yeah, I guess you have to define it that way. All right, yeah, all right, but it's just sort of playing games with definitions, right? We haven't really done anything, right? Turns out you have to do something if you want to do a directional derivative, but not of a function of a vector field. Okay? And so, what if you have... Okay. And so we're not going to do this on the surface. We're just going to do it in 3 dimensions. So imagine you're in 3 dimensions, and just reviewing your multivariable calculus. And you have a vector field. Everybody remember what a vector field is, right? We've been talking about them a bit, but let's say you have 2 vector fields. One is u and one is v. Okay, so I've drawn a vector field, but imagine you have 2 vector fields. And then there's the question of what is a vector field? U has components. Let's number them. I'm trying to remember what if the book actually does this, but let me go ahead and introduce some new notation for you. Okay. So there you might say, what do the 1, 2, and 3 represent? Well, it's like the x, y, and z, but we're numbering things like grown-ups. The X, Y, and Z is an artifact of your multivariable calculus training, right? It's like, because, why would you ever want to go greater than 3 dimensions, right? We'll just call them X, Y, and Z. But even that, even if you only wanted to stick in 3 dimensions, isn't it a little bit better to say the first dimension, the second dimension, and the third dimension? Isn't that? Because, it's using numbers instead of letters, right? And, of course, when we go to higher dimensions, you run out of letters, right? Okay, so you're going to so this means U, X, U, Y, and U, Z. That's all it means. Don't be thrown by that. And then you might say, okay, well, how do I take the directional derivative of a vector field? So what is the definition? Let's say if I have another vector field V, then this is the directional. This is, by the way, they don't use the word directional derivative. They use the word covariant derivative, but it's the same concept, covariant derivative. Now, why do they call it the covariant derivative? It's because mathematicians don't have friends.
What?
I'm being silly. It's because we don't have enough friends. It's because we sometimes call things stupid things for no good reason. There's no particular logic behind the word covariant derivative. The logic used to be that, well, it's because of the way things transform. Some things can transform like a vector and some like a covector. So some of it's like, they kind of came up with these terms, transforming contravariantly versus covariantly and blah, blah, blah. So it was a covariant derivative instead of a contravariant, blah, blah. Turns out they got it wrong. It's actually a contravariant. I don't know. It was just big, messed up confusion, okay? And so it's historical at this point. They call it the covariant derivative because they call it the covariant derivative, okay? And it is slightly annoying because, it should be called the vector derivative, okay? It should be called the vector derivative. That would be a reasonable enough notion. The key point to understand is it's something different than a directional derivative. It's not the directional derivative, okay? Because what we're trying to do is we're trying to take the derivative of a vector field in the direction of another vector field. And that sort of seems like a directional derivative, but it is really a completely different beast. Okay, and that's the main thing you have to remember. And so now, how do we do it? Now, you did this all the time in multivariable calculus. You took derivatives of vector fields in the direction of other vector fields. And the reason you did it is a vector field with just 3 functions, right? U1, U2, and U3, or Ux, Uy, and Uz. And so what you simply did was exactly what you're thinking, which is you take you use your directional derivative there, and you simply take the directional derivative of U1, comma, the directional derivative of U2, comma, the directional derivative of U3. Okay? And so yeah, that's our definition of covariant derivative in R3. So this is the covariant derivative in R3. Let me just distinguish that, okay? You could also do it in R2 or R1, whatever. I just want to point something out. This definition does not work. If you have a vector field on the potato and another vector field on the potato, that definition doesn't work. Because the reason it doesn't work is see how it requires 3 dimensions? And the mathematician ant on the potato has never heard of the 3rd dimension. It's like, what are you talking about? So far, now, if they're a genius mathematician ants, which I've said they were, they know how to take covariant derivatives. It's just not this way. Okay, and the point is, this makes no sense to them. They know how to do it. But it's actually a rather complicated formula that you haven't learned yet. And I will teach it to you by the end of this class, but it's not even in the book. It's really in the 2nd course. You realize it's in the 2nd course for differential geometry, how to take derivatives of vector fields in the directions of other vector fields. Right, that's how advanced it is, right? And I will show you that advanced topic at the end of this class. But this is like something kind of interesting, actually, right? To do intrinsic geometry of the covariant derivatives. Would you agree, Lily? Yeah. Okay. So it's something called the Koszul formula, K-O-S-Z-U-L, and you can look that up. It's also known as the Levi-Civita connection, right? So when you got multiple names associated with it, it's complicated. Yes.
I remember earlier you said maybe it was Einstein who started putting the numbers above the letters.
Oh yeah, that's Einstein
I
notation.
don't remember if you explained why, because I feel like I've always learned.
By the end of this class, I will tell you why you use superscripts and not subscripts, but not right now. But Einstein, that's called Einstein notation. There's also something called Einstein summation notation. But the Einstein notation makes sense. It makes it easier to remember what to do when and how things transform. And it says its sole contribution to mathematics, by the way, is Einstein notation. Yeah, he never proved the theorem, but he did come up with that notation. Yes?
What exactly are you doing when you're taking the derivative of a vector field with respect to another vector field?
I mean, it's just, this is just a definition, all right? But really it's saying, it's just what's the rate of change of u if we were to follow a curve in the direction of v.
Rate of change.
So for example, if u is a constant vector field, then this would be 0, right? And if these are just three directional derivatives, so it's just the, in that sense, it's the rate of change of the vector field u in the direction of v. So as long as you're in 3 dimensions, and then this definition seems perfect, is very reasonable, and you used it in your multivariable calculus class. And but it's really a definition. It's the rate of change of each of the components, you actually might say. But like, what does that represent? Well, it comes up in formulas and stuff. It's a little hard to imagine, right? It's a little bit easier with a real valued function, but this is a real valued function, and that is too, and so that's just 3 of them. Right? But then this allows us to come up with one of the central objects of study in this course, and it's called the shape operator. And now the course begins. Okay, if you were kind of wondering, when was it going to start getting interesting? Okay, and you're like, oh, this is too easy. Now this is beautiful, is what this is. Okay, we're just like, I know it's not too easy, but it's a lot of definitions and stuff like that. Here's where it starts to get really cool. So I'm about to show you something beautiful. And it's the shape operator, and it's one of the central concepts in this class. So what you do is, suppose we have our potato here, right? And here's your tangent plane, your point P. And it turns out that the shape operator is an operator on the tangent plane. And it maps the tangent plane at the point P to the tangent plane at the point P. Okay? Now you see how I've drawn this plane to be flat, sort of like the xy plane? But do you know the other tangent planes aren't flat? They're not like the xy plane at all. I just drew it because it's easier for me to draw the picture. Maybe I should have drawn it at an angle, okay? Just to emphasize. It's just some plane, okay? There is no canonical way to say which way is the x direction and which way is the y direction. I'm going to give you an example of a mapping from a plane to a plane. Okay? And, well, how do you do this? Well, it uses this unit normal vector, right? Remember you have this unit normal vector u, and it's defined everywhere. It's perpendicular, right, to the surface everywhere, right, pointing out. And we were computing it last time, in fact. And I won't draw it, but you can see it varies from point to point, right? And so what we're really interested in the shape operator, what we're trying to do is get a sense of how this thing is curving, right? And so it turns out there's a very natural idea of how this thing is curving, and that is, you say the way that the rate of change of the curvature, right? Let's say I have a vector v here. Typically it's a unit vector, but I guess it doesn't have to be. If I want to understand how fast is this potato curving as I go in the direction v from the point P, right? You can see it's definitely curving, right? How do you know it's curving? The way you know it's curving because u is changing. And so you say, oh, I know what the curvature is. It's just the rate of change of u in the direction of v, right? Oh, okay, so the curvature in the direction of v is the rate of change of u. So that's what we're going to do. The definition is you simply take the covariant derivative in the direction v of that unit normal vector, capital U. Okay? And then for historical reasons, you put a completely arbitrary minus sign right there. Just historical reasons. Completely arbitrary. Okay, it's too late to change now. Everybody does it that way. Now, that seems like a perfectly reasonable definition of curvature, because it's the rate of change of u but now what we see is we have a notion of curvature. It depends not only on the point P, but also the direction you're going. Right? So if you change v, you're going to get a different answer here. Right? So it's a function of not only your position, but also your vector. Yes?
What does it mean when you say that it maps TP of m to TP of m?
Great question. because I made that claim, but so far it's not at all obvious that's true, right? Because, I mean, okay, look. I want you to grant that this function only makes sense if v is in the tangent plane. I can't take derivative of u and get off the potato, right? It can only go in the direction. U is only defined on the potato. So clearly, this v has to be an element of the tangent plane, right? Otherwise, this doesn't make any sense, right? Because u is only defined on the potato, right? And if you want to be really, even that point, there's a little bit of an issue here, right? Because this tangent plane and the potato are not the same thing, right? If I go in the direction of v, technically I'm getting off the potato a little bit, aren't I? So actually, you might even say, does this even make sense, right? If the potato curves away from the tangent plane, right? Turns out it does, okay? But how do you fill in the details? What you do is you assume everything is smooth. That defines u on the potato, right? And then you say extend u smoothly up above the potato and into the potato three-dimensionally, okay? Smoothly. And then you do this definition. And then you prove it doesn't matter how you do the extension. Okay? Because this really is only, it's because the tangent plane approximates it well enough, right? It's curving off a little bit, but it doesn't matter. And so really, the rate of change, if you were to compute a second derivative of u in the direction of v, then that curvature would matter, right? But the first derivative it doesn't matter how you sort of extend the definition of u above and below the surface of the potato. Okay, so it turns out this is well defined. But then there's this trick I told you guys about that we're going to use like 17 times in this class, probably more like 1,700. And that is that, remember 1 is equal to u dot u? Because it's a unit vector. And now let's take the derivative in the v direction. You'll see what I did? I just want to take the directional derivative, right? Of both sides of the equation. Of course, directional derivative of 1 is 0. Now, what's the directional derivative of u dot u? Well, guess what? It's just the product rule. You all remember the definition of the dot product, right? And so the product rule with directional derivatives combined with this definition here, right, means what we're going to get is just 2 u dot product, and then that definition right there, a covariant derivative in the direction of v of u. Okay. And then you stare at that. I mean, y'all believe that, right? It's the chain rule. I mean, it's just the product rule. And then applied, and then you with the definition of dot product and that definition of covariant derivative, that's what you get, right? Right? Because, I mean, what is this? This is u1 dot u. This is u1 times u1 plus u2 times u2 plus u3 times u3, right? And so you work it out, and that's what you get. Right. Derivative of u1 squared is 2u1 covariant derivative of u1, right? So that's the dot product of the first term, right, and so on. And then you're like, wait a second, the dot product is 0, so they're perpendicular, right? So this implies that this right here is perpendicular to u. Well, wait a second, you have a vector that's perpendicular to u? Isn't that the definition, one of the definitions of the tangent plane? Yeah, use the vector that's perpendicular to the tangent plane. So therefore, this covariant derivative of v of u is also an element. And also when you put a minus sign, also this changes direction. That's an element of the tangent plane. So sure enough, we have a mapping from the tangent plane to the tangent. That's the shape operator. Super cool.
Why can't that be above the plane? If it just has to be perpendicular to u, that doesn't really prove that it's on the plane. It could be parallel to the plane.
So all the vectors we're talking about, so when we talk about a vector, its base point could be anywhere, right? So a vector we're thinking of as just as a displacement. So if you think of it, so the way to think of it is all the vectors we're talking about are based at the point P, right? Okay. And so if you're perpendicular to u, it means you're perpendicular to so in other words, what a vector is if you think of a vector as a displacement, then in that sense, this vector, see, I haven't actually drawn this vector anywhere, right? But the point is, these vectors are all the same. Is that the question you're asking? Okay. Yeah. So as a displacement, it's perpendicular. Yeah. So in some sense, we're always thinking of a vector as the tip minus the tail. Good question. Other questions? But then what you see is it's a mapping from the tangent plane to itself, and so, oh, that's linear algebra, isn't it? So we've got some linear algebra to do, don't we?
Changing bases.
Well, I mean, there's all kinds of stuff. We're going to have lots of fun with this. We're going to definitely change bases, and but when you have a mapping from a vector space to itself, there are some basic quantities to study. Don't ever forget the definition of directional derivative, by the way. Can y'all promise me this? Sure.
What are we promising?
Someday, when you're 90 years old and you have dementia. No, someday when you're 90 years old, you will not have dementia because your entire life you will have been reminding yourself the definition of the directional derivative in case I show up and ask you and pop quiz you. What is the definition of a directional derivative, right? It's the derivative along a curve, right? That whose velocity vector is that direction.
This is why mathematicians don't have friends.
Yes. No.
But are you still going to be alive when you're 90 years old?
I like to say positive. Directional derivatives. Actually, I think this is why. You know what? Actually, we have all the friends we want. We just don't want that many friends. This is kind of the problem, because we're happy with our mathematics already. Like, we have everything we need. I hope math. If someone put me in jail and they gave me solitary confinement, which is supposed to be this horrible punishment,
It just means you're introverted.
I'm just going to get a lot of work done, okay? The point is, I'm just going to get a lot of work done. I'm going to be proving theorems. It would be great for my mathematical career, okay? And I wouldn't, I think I would entertain myself. And actually, it's a great joy to be a mathematician in that sense. And so I hope that y'all, a little part of yourself anyway. Like, you don't need to go full, math nerd, right? You can decide where you want to draw the line exactly, because I'm half joking, right? Because you do want to have friends and you do want to have a social life. And I'm married with 6 kids, okay? I have, I'm a social person, right? But I also know how to enjoy mathematics. It requires extreme concentration, and we sort of withdraw from the world when we do that, right? And that's a great skill to have. But also, I don't think you're going to get dementia as much or as badly anyway if you keep remembering the definition of directional derivative. Like, you never forget, or the definition of the shape operator, right? If you can remember this stuff, it's like throughout your life, remind yourself and continue to be curious and learning, right? And use your brain. Use it or lose it. That much has become, I think, look, we don't know this scientifically yet, but we know, it makes sense with muscles, right? Like, if you don't exercise, you're going to atrophy, right? And if you don't work out your brain, you're going to atrophy. And that's not to say there aren't genetic diseases and it's horrible and so forth, and some people can do anything about it, of course, both with physical muscles and their mental prowess. But nevertheless, I think really enjoying learning, right, is good. It's important for your long-term health. That's what I'm trying to say. I actually mean that quite seriously. Okay, let's do an example. Let's say M is a plane. Okay, so you have some plane here, right? The Newton normal vector is the same everywhere, isn't it? Perpendicular to the plane everywhere. It's constant, right? And so when you say, what's the shape operator of a plane? This is just the negative covariant derivative of that unit normal in some random direction. Well, guess what? The unit normal is not changing, so no matter which way you go, it's 0, right? Shape operator is 0 for a plane. So it's still mapping from the tangent plane to itself, but that it's a 0 vector, by the way. It's not the 0 number, it's the 0 vector. So that's example 1. Example 2, let's say M is a sphere. Okay? So let's take, by the way, always draw the sphere first. Then you draw your coordinate axes, right? And we can do a sphere radius r just like we did before. And now we computed last time the coordinates for the sphere. So let's pick up from last time. So I think it was last time, right? And this unit normal u equaled cosine u times cosine v, comma sine u sine v sine v. You guys can check me. Hopefully, I think that's what we got last time. And so then when someone says, "Hey, what's the compute the shape operator in the xu direction?" And this is in the book, by the way, so you don't have to take super careful notes. It's all in the book, right? Actually, it's one reason I follow the book as much as possible. I'll tell you when I'm not following the book. Well, by definition, it's the negative covariant derivative in the xu direction, right, of u. Now, this u, on the one hand, is a vector field that depends on x, y, and z. On the other hand, conveniently, it's already expressed in terms of u and v, right? And so we know, remember that thing I said before? It was right here. I erased it. I think you can almost see it. Yeah, it's like right here, right? And remember I said that when we take the derivative in the xu direction, that's the same thing as just taking a partial derivative. In other words, I can just do that. Y'all remember? Okay, and we proved that. And so what is the partial derivative? So in other words, I can just look at this u here and take a partial derivative with respect to u. And that is the covariant derivative. And so what we have then is...
the second term has a cosine v.
Oh, thank you. Right here is cosine v?
Yeah.
Thank you. Boy, who did that? Thank you. Yeah, it's right here in my notes, cosine v. Thank you. Okay. And so now we just take a u partial derivative. And I'm going to go dot, because it's just calculus, and you guys know calculus quite well. And it turns out now we almost skip calculations, but put in what we get. What we get is sine u, just the negative of the u partial derivative, right? Okay, so sine u cosine v, comma, negative cosine u cosine v, comma, 0. Okay, does this seem right? So it's the negative u partial derivative. So the derivative of cosine becomes a minus sign, but with that negative becomes a plus sign. Cosine v. Of course, the u partial derivative of v is 0. And sine u cosine v, take the u partial derivative to get a cosine minus cosine. Right, because that minus sign there. And then from last time, by the way, this actually equals a vector we already recognized, which is negative xu over r. So I won't work it again, but remember we parametrized this sphere in spherical coordinates, and we computed xu, and it turns out this, in fact, is in the same direction as xu, and it equals negative xu over r. Okay. And then you do the same computation, and it turns out for the sphere, the shape operator of s applied to xv, you do the same computation we did just right here, and it turns out this equals negative xv divided by r. Okay? And you're like, oh, that's an interesting coincidence. What does it mean? Well, these two things put together imply that the shape operator of a sphere, when you put any vector v in there, it just means multiply it by negative 1 over r. This is what we get. This is true on a sphere. Sphere of radius r. You just multiply the vector by negative 1 over r. See, we verified this on a basis, right? And so if it's true on a basis, it must be true on all vectors. Now, what's the proof of that? Is, if you want to, actually prove stuff, right? You remember, to me, step one is it should make sense. Step two, you prove it. I mean, it's kind of like a back and forth. Sometimes you prove it first, but then you're like, but why is that true? Is that really true? Do I believe that? And it's got to make sense, right? So if you have a linear mapping, first of all, is this a linear mapping, right? Yes, it turns out this directional derivative, we know that the directional derivatives are linear. It's linear in V, right? If you can see if I were to double V, right, then it just doubles the derivative here, right? And also, if, covariant derivative of V plus W is just going to be, this will be V plus W, and it's linear, all right? So you can verify that. So, and so I have a linear mapping, and it does the same thing to two different vectors. You say, okay, it probably does that to all the vectors, as long as these vectors are linearly independent. But how do you prove that exactly? Well, you take any vector V, and therefore it's, assuming XU and XV span the tangent vector, then that vector V is going to be some linear combination of XU and XV, right? Fair enough? I don't know what A and B are, but whatever. And so then when I say, what's the shape operator of V? Well, because the shape operator is linear, first of all, I just plug all that stuff in there, right? AX U plus BXV. Well, because it's linear, this is going to be SP of this plus SP of that. And then the A and B's factor out, so it's A of SP of XU plus B of shape operator applied to XV. And then this is equal to, by definition, the whole point is what we already know it does XU and XV, it multiplies them by minus 1 over R, right? And so I get A times XU over R plus B times XV over R, and then multiply everything by a minus sign, right? And then this is equal to, factor out the negative 1 over R, AXU plus BXV, but AXU plus BXV is V, so this is negative V over R. Okay? This is what you call bad board work. When equations are going up. Right? Kind of reminds you of your homework, perhaps. Right? Anyway. My apologies. Try to do better. I should do better. For the price you guys are paying. Any questions? All right, so that's an example of complete the shape operator. So so now I guess you're convinced that we have, in fact, a linear operator. It's something that sounds pretty fundamental. It has something to do with the curvature. Any questions about this sloppy computation? I'm inclined to erase it. Okay, so we'll get into some more examples next time, prove some more theorems. But if you have, again, we're talking about the shape operator. And so when you have linear mappings, okay, linear mapping from a plane to a plane, there are two basic objects that you learned in your linear algebra class. And you remember what the two most important things about linear mapping are? Or let's say two very important things. Like, if you have a linear mapping, what are, I'll give you a hint, they're real numbers. There's two real numbers associated with linear mappings that you talk about quite a bit. At least one of them you talk about quite a bit. Yeah?
Trace and determinant.
There you go, trace and determinant. It's because they're invariants. So when you have a mapping of a vector space to itself, you can talk about the trace and the determinant of that mapping. In other words, you can say, what's the determinant of this shape operator? And what's the trace of this shape operator? We're going to have names for these things. And I'll remind you about how to take determinants and traces later, right? But the determinant, we're going to use the capital letter K for that. We're going to call it the Gauss curvature. And it turns out this is intrinsic geometry, believe it or not. And when we take the trace, we're going to call this 2H. We're going to call this H there is called the mean curvature. So this is the Gauss curvature, which I guess might be the central object of this course. And this is H there is the mean curvature. The Gauss curvature here is intrinsic. This is something that the ants understand. Now they have to be genius ants. Okay? Because they can't compute the shape operator. Shape operator makes no sense to these ants. Okay, they have no idea what you're talking about when you say the shape operator. Why? Because you're talking about this three-dimensional vector u going perpendicular to the potato in the third dimension. They're like, what the hell are you talking about? Right? So everything we've done in this lecture doesn't make any sense to the ant. However, they have other ways, other formulas, these genius ants, of computing this intrinsic quantity here, k. Turns out that is not, even though we can define it, so far we're defining it using the extrinsic geometry of the shape operator, right? So the shape operator here is extrinsic. But by some miracle, it so happens the determinant of this extrinsic geometry object is actually intrinsic. Okay? The trace, though, this is still extrinsic. Most things, everything, in fact, everything else about it is extrinsic curvature. Okay? The only thing that is actually intrinsic is the Gauss curvature. And now let's just see why this makes sense. You guys ready? Take a piece of paper here. Y'all see how pretty much, I can make any cylinder out if I want. Here's like an S cylinder, right? Do y'all see that the normal vector here? Can you visualize the normal vector coming out of the piece of paper? It changes when I go this way, right? But it doesn't change at all when I go along the spine here, right? So the shape operator along this direction is actually 0, right? Because the normal vector is not changing, right? When they change the normal vector, it's the shape operator, right? And so the shape operator in this direction is 0, which means one of the eigenvalues of the shape operator is 0. Okay? Do y'all remember that the determinant is the product of the eigenvalues? Okay. So that means that the determinant of the shape operator here is in fact 0 everywhere on this piece of paper. Right? And so the determinant is actually 0. And this is intrinsically flat. And sure enough, you can fill up this piece of paper. Even if you're an ant, you can draw little squares and stack it with squares, make graph paper, right? And the intrinsic geometry is 0. What's interesting is imagine you took like a top half of a sphere that's made out of, let's say, a flexible material that won't stretch. Okay, so it's sort of a, think of it as a kind of a plastic, right? Actually, I love it. There's certain toys my kids get for Christmas, and they're like spheres, but they have this shrink wrapped plastic comes on them, right? And of course they rip them off to get to the surprise on the inside, like an egg of some sort, right? But then I look at this plastic and it's a perfect sphere, and I'm like, it's pretty fun. I actually have some in my office, right? If you ever want to kind of check it out, I think. If I didn't throw it away already. But the point is, you can take that spherical geometry, you can squeeze it, and the equator becomes an oval. Like you could take just the northern hemisphere, right, and cut it along the equator. You can squeeze it and make the equator like an ellipse. But the point is that the extrinsic geometry is changing, but the intrinsic geometry is staying constant curvature the whole time. Right, and so and the K is not changing. Now the H is. Everything else is. And what is this K? Let's just talk about this K for a second, because to me it's like the most interesting thing. Well, what is determinant? Determinant. Here's an interesting thing. Let's see if we can do this real quick. Okay, I'm going to draw a picture. Okay, I'm in a hurry, so I violated my rule, so my sphere is off by a little bit here, okay? Let's think of this mapping here. This is, oh gosh, what's it called? The Gauss map, I think they call it. So let's do a mapping from some potato here, okay? Call it M. To the unit sphere here, this has length 1. And the mapping will be U, okay? Now U, yes, U as in the unit normal vector, okay? Now I want to point out this unit normal vector has length 1 everywhere, right? So if I take all these u's and then just translate them to the origin, right? That's a u. This is a u, right? You know, what's the u here, right? That has length 1. I can translate it to this vector right here, right? So then this point here would map to that point there, right? And then this point here has this normal vector, and so it maps to this point here. So y'all see we have a mapping then. This u maps your surface M2 into S2. I think it's called the Gauss map.
Must be convex.
We're not assuming anything this is convex, but okay, I think let's assume it's convex for right now for simplicity, right? Actually, let's do that. Let's assume this is convex. It'll help with the mental picture. Turns out it doesn't matter. So think of this as a convex thing, then especially if this was a sphere, it would be the identity map. But this is the unit sphere, it's the identity map, right? Fair enough? Because the unit, each point, but let's say it's some perturbation of that, there's going to be some perturbation of the identity map, right? Yes?
What if there are 2 points on the potato with the same unit normal?
Well, that won't happen in the convex case, right? But turns out it won't matter for what I want to do, but it's, let's not think about that right now. So imagine that's not the case. We'll say it's like convex. Strictly convex, in fact. Okay, perturbation of a round sphere. Then what is the determinant? Do y'all remember when you have a map? So when you have a mapping, how much volumes and areas get stretched, right? Comes from the determinant of the Jacobian, right? Well, this shape operator is a determinant, right? And it turns out it tells you exactly how much areas are being stretched when you go from here to there. I mean, if this is curving really fast, right, then that means a small area here gets mapped to a really big area over here, right? And so in particular, the volume form, or the area form over here, let's talk about the area form over here, and let's talk about the area form over here. Well, I'll say DAS2, okay? And this is DAM2. And it turns out that dA of M2, what's the relationship to that of the area form? These are the things that you integrate along the surface. If I integrate this, you get 4 pi. Okay, that's the definition. Turns out that this is bigger than that, and what the factor is the k. Okay, k is the stretching factor. So I can say this equals that. Okay. You know, if you correspond to the corresponding regions, right? In other words, if I integrate this over the whole M2, this is equal to the integral of this over the whole S2. Okay. Again, imagine it's 1-to-1 on 2 for right now. It's like it. But this, remember what the area form is defined to be. It's exactly what is the surface area of that sphere of radius 1, which is 4 pi. And now we've just written down the Gauss-Bonnet formula for the first time in the simplest case, which is that the integral of the Gauss curvature over a spherical surface is always exactly 4 pi. And there is this intrinsic geometry has this amazing property that when you integrate it over a sphere, it's always 4 pi. Now that y'all both anticipated, well, what if it curves back on itself and it's not a 1-to-1 mapping and blah, blah, blah. Turns out this argument is still correct. This is still true. Okay. But here's the kicker. The kicker is this actually does depend in an important way that this surface is topologically a sphere. And more generally, you don't get 4 pi. If this were a donut, surface of a donut, you get 0. And if it was a donut with 2 donut holes, you get negative 4 pi. And if it was a donut with 3 holes, like, you know, so you make sure you understand what I'm saying. Yes, this is what I mean. A donut with 3 holes. So surface of genus 3. Then you would get, let's see here. You have to subtract 4 pi for each hole, right? So that gives you 4 pi. That gives you 0. This gives you minus 4 pi. And therefore that gives you minus 8 pi. And more generally, it's, excuse me. Yeah, 1 minus the number of holes. The holes is called the genus G. And that's one of the simpler versions of the Gauss-Bonnet. Now, how do we prove that in general? That's going to be more interesting, and that will be sort of the center of this class. Maybe is like, or maybe the highlight of the class is proving the Gauss-Bonnet theorem. And that's a little bit involved. I can't do it right now, but it's beautiful. And this is something the mathematician understands because it's all intrinsic geometry. And I guess if I had to pick one theorem in mathematics that was my favorite, this one would be on the short list, right? In some sense, this is a special case of something called the positive mass theorem, which is my favorite theorem in mathematics. It's a math theorem that basically explains why when you jump up, you come down. Why gravity is attractive. So it's important in general relativity. But if you ask what is the positive mass theorem in dimension 2, it's the Gauss-Bonnet theorem. So this is a deep theorem that's important. All right, so you guys can look on the homework. We'll do examples next time. I'll show you properly.